Hi everyone. I'm delighted that we have Minki Hong joining us today. It's a really exciting presentation. So it's a continuation of the theme of using material discovery, machine learning to do material discovery in the OLED space. And Minki is going to tell us about how to deal with clean and dirty data simultaneously to discover new OLED material. So you have 15 minutes. The stage is yours. 2 minutes before the end, I will try to intervene just to give you a heads up. But otherwise, please start.
All right, thanks so much, Kasha, for the nice introduction. So I'm Minki Hong from Kyulux. Today I'll talk about how we been using machine learning to develop our molecules. So for those who don't know, the Kyulux is a spin-off company from Kyushu University in Japan. We established back in 2015, and a year later we established Kyulux North America. So a Japan team most likely responsible for experiments, and North American team responsible for computational matters. So all the machine learning works we've done so far is done by the Kyulux North America, where I am. So we are trying to develop the emissive material that's used in OLED devices. So I'll just skip this thing. So OLED device can be divided categorized into many generations over time. We currently focus on so-called hyperfluorescence devices that try to harvest all those excitons, the 100% to the up to 100%, but actual emission is happening through the fluorescent channel. So we call that as a hyperfluorescence. So I think most of you are well known about the basic idea of utilizing machine learning, in trying to find a good molecule. So we have the similar ideas. So our goal is again try to make a good emissive molecule for OLED, and to do that we establish so-called materials informatics system within the company. We call it as a Kymatic. So the scheme is pretty simple. So when we have a new ideas and we run a so-called high throughput virtual screening using some computational methods, and we actually synthesize those molecules. We select some of them, actually synthesize and test, and we then make the actual OLED devices and then test it. And all those experimental results feed back to the idea and becoming new idea. So we have this sort of circulation of the ideas. So far we have accumulated data, so more than 236,000 molecule, and we have calculated those molecules, and out of that we actually synthesized 1,000 molecule, more than 1,000 molecules. And then out of those molecules, we actually fabricated more than 6,700 devices, which has a unique structure. So if we just count all those duplicates as well, it actually more than 17,000 devices. So these are, I would say, more cultivated data only for OLED. So it's a very unique data. So we really try hard to utilize these computational and experimental data at the same time, and try to use the machine learning to use both of them. So let me give you a quick overview of what kind of a model, machine learning model we've been using so far. So you can have three categories. The first one is that we called calibration. So this model is trying to map between the DFT results to the corresponding experimental results. So for instance, we can calculate directly from DFT calculation the HOMO of the molecule, and we can measure that as well. So because we have experimental data, we try to match those two things. And as you can imagine, over time, we add more data. So